Hey there, and welcome to This Explainer. If you've ever looked at just a massive jumble of fractions, decimals, and square roots and felt totally overwhelmed, well, you're in the exact right place. Today, we are completely demystifying the universe of real numbers. We're going to build a clean, easy-to-understand map of how every single number out there relates to the others.
Okay, to get us started, I want you to imagine this giant, messy pile of numbers. We're talking positives, negatives, weird fractions, and those decimals that just seem to go on forever. Now, if you reached in and pulled just one specific number from that pile, let's say the square root of 3, where exactly does it fit? Is it a fraction, an integer? Well, to solve that mystery, we actually need to build our number universe step by step, starting from the absolute basics and expanding outward. All right, let's dive into this with our very first building block, natural numbers. Think of these as literally the simplest numbers out there. They're the ones we naturally use when counting physical objects, right? Like 1, 2, 3, 4, and upward to infinity. They form the foundational core of our whole mathematical universe, completely free of any fractions, decimals, or negatives.
So now we take that core and add just a single layer of complexity. Whole numbers are simply all of those natural counting numbers we just talked about, plus the number 0. It seems like a super tiny addition, right? But honestly, introducing 0 was a massive leap in mathematics. Actually, think of our number system kind of like nesting dolls. The natural numbers sit perfectly tucked inside the slightly larger whole numbers doll.
Let's expand those boundaries once again to create our third nesting doll, integers. Now we're venturing into the world of opposites. Integers include all of our whole numbers, so 0, 1, 2, 3, but they also bring in their negative counterparts, like -3 or -7. Now notice, we still don't have any fractions or decimals here. It's really just clean whole steps in both the positive and negative directions.
Okay, now here is where we finally break the spaces between those whole steps. We've arrived at rational numbers. A rational number is basically any number that can be neatly expressed as a fraction, a ratio of two integers, which we usually call p over q, as long as q is not 0. So this includes fractions like 12 over 21. But importantly, it also includes decimals. Specifically decimals that either neatly terminate, like 1.5, or predictably repeat forever, like 0.333, which, as we know, is just 1/3.
And this brings us to a really fascinating divide in our number universe. On one side, we've got our rational numbers. As we just saw, these are neat, they're predictable, and they can always be tamed into a simple fraction. But, on the other side, we have the chaotic rebels of the math world, irrational numbers. These are numbers that absolutely refuse to be written as a simple fraction. They are decimals that just keep going on forever and ever without ever forming any sort of recurring pattern.
To really ground this abstract concept, let's look at probably the most famous irrational outlier of them all, pi, 3.14159 and on and on and on into infinity. You literally cannot write pi as a simple fraction of two integers. It never terminates and it never ever settles into a repeating loop. It is just beautifully, infinitely chaotic.
So let's really cement this definition before we bring all the pieces together into the big picture. Irrational numbers are real numbers that cannot be written as a simple fraction. They are decimals that just do not terminate or repeat. So alongside pi, this category includes things like the square root of 2 or a completely random, messy decimal like 3.2576. They sit entirely apart from our nice, predictable rational numbers.
And this brilliantly illustrates how the whole nesting doll analogy comes to life. Picture it. Wrapped up in a large rational number space, we have our smaller subsets, right? Integers sitting inside rationals, and whole numbers nestled safely inside integers. Every whole number is an integer, and every integer is a rational number. But taking a step back, the irrational numbers have their own completely separate space. They share absolutely no overlap with the rational numbers. Though, when you put them all together, the whole shebang makes up the entire universe of real numbers.
Let's reinforce these boundaries a bit. Take a fraction like 2/3. Because it's a ratio of two integers, it lives safely in the broader rational numbers area. However, it sits outside the integers and whole numbers groups because, well, it isn't a clean, whole step. And notice how it is completely separated by a hard wall from the irrational numbers. No mixing allowed.
All right, now that we have our map, how do we actually organize a messy pile of numbers in practice? Well, we methodically follow 3 powerful classification rules. Step 1, always simplify your fractions or radicals if possible. Step 2,
determine the absolute most specific classification for that number, its smallest nesting doll. And step 3, remember that the number also belongs to any broader set that contains that specific classification. Now, you might be wondering, why does this even matter? Well, organizing numbers precisely like this is literally the bedrock of everything, from computer programming and cryptography to the intense engineering precision required to, say, build a skyscraper or launch a rocket. You absolutely have to know exactly what kind of data you're dealing with.
So the crucial point here is really that first step. Honestly, it's the ultimate trap. You always have to simplify first. For example, if you see the square root of 36, your brain might immediately jump to the irrational category just because it has a radical. But wait, actually scratch that. The square root of 36 simplifies perfectly to 6. And 6 is just a simple, basic counting number. So its most specific classification is actually a natural number. If you're a visual learner, using a logical flowchart is a truly fantastic way to track this. You just follow the logic straight down. Is it a real number? Can it be written as a fraction? The second you hit a no, boom, you found its category. If the answer is yes, well, then it's rational. And you just keep asking questions. Does it have a decimal part? Is it greater than 0? Following this logical path guarantees you're going to drop your number into the exact correct bucket every single time.
Okay, let's walk through a practice set together to really lock this in. We already caught the trap with the square root of 36. Since it simplifies to 6, its most specific home is with the natural numbers. Next up, 0. It's not a counting number, but it is the defining addition to whole numbers. What about -7? Well, that negative sign pushes it right out of the whole numbers and specifically into the integers. And 1.5? That's a terminating decimal, which means it can easily be written as the fraction 3/2, making it specifically a rational number.
Let's move to another mixed pile and see how this all builds together. 10 divided by 2 looks like a standard rational fraction, but remember, always simplify first. It's really just the natural number 5. 4 is obviously already natural. -3.7 is a terminating decimal, so that makes it rational. And finally, we return to the question that started it all, the square root of 3. Well, it can't be simplified, and its decimal goes on forever without repeating, so it firmly belongs in the irrational category.
So there you have it. We've taken an infinite, completely messy pile of numbers and organized them into a perfectly logical system. But before we wrap up this explainer, I want to leave you with one final provocative thought. We've successfully mapped out the universe of real numbers, but what happens when you square a number and the result is negative? Like, what happens when numbers get imaginary? Well, that bizarre reality is a completely different map and definitely a topic for our next explainer. Thanks so much for joining me today.